morning, ladies and gentlemen, and happy warm welcome to the presentation of mine about my thesis, which has the charming title, Is the Electric Power Landscape Shifting Towards a Closed-Loop Supply Chain? And there we have already the main two ingredients of this thesis, which is supply chain management on the one hand, and electric power, electricity on the other hand. So this is today's agenda, for which I would like to walk you briefly. And if you think about it, supply chain management and electricity management are not too different. If you look about the process steps, which usually are involved, it starts from the production plant or supply chain management side. Then the goods, what is being produced, is shipped throughout the company, throughout the country. It is transmitted until it finally reaches the customer in one way or another. Well, now pretty much the same is happening for the electricity side. We got generation plants which are producing energy. It is being transmitted and distributed throughout the country until it finally reaches the socket. I don't know where we have sockets. There is a socket in this room, otherwise we have sockets and out of which we just take electricity. So in both cases, it used to be like a unidirectional flow of goods from A to B, from generation to consumption. And both industries, they share many common things, common themes. They use similar techniques, they use similar tools and mechanics, and they face a similar environment. And what they also do is they face a similar development. Because what started like 25 years ago for supply chain management is that goods were not only going from A to B, so from sourcing to consumption, and that's it, finished. No, but people were increasingly returning products. So they go from A to B, and then maybe to C, and then back to A, to where they come from. And this has led to the creation of reverse logistics, which is triggered by laws, by economic incentives, and this has made customers to increasingly return the products. And to address these challenges, which result from these developments, the theory of closed-loop supply chains has been developed. So the theory says, well, as many ingredients we have a forward supply chain, we have a reverse supply chain, and both flows are fine-tuned to one another, and the customer takes a very critical role. Well, to address these challenges, which started 25 years ago, we have established the theory of closed-loop supply chain. And pretty much the same is happening now for the electric power management side, where people are not only taking electricity out of the socket, but because they have a solar panel on their roof or a biogas installation in the basement, they are feeding electric power into the grid. So there as well, we just don't only have these unidirectional flows of goods from A to B, but people are feeding electricity into the grid. So this resembles the flows which we have on the supply chain management side. Now, the question is, if we have this development for 25 years on the supply chain management side, but it only started a couple of years ago on the electric power management side, what can we then infer for this electricity movement? Where is it going to develop? And this is what I would like to answer. So I'm drawing on these 25 years of experience which supply chain management has in dealing with these reverse flows, and I see what can be inferred for the electric power landscape, which is facing a similar development. And of course then we have to adapt the typology, terminology, because there are different pivotal topics on the electric power side. So for example, this whole development was triggered by renewable energy sources, and it found also expression in distributed generation, which means that instead of large and centralized facilities, you have like small-scale generation units, like photovoltaic systems. So these are the pivotal topics, and then we can ask, what are the implications for the grid? And which role do the prosumers play? And prosumers are producing customers, so therefore you speak of prosumers. So these are the people who have a solar panel on their roof or the like. So these are the pivotal topics which trigger this development in the electric power side. And by applying closed-loop supply chain theory, we can sketch the transformation and see what is going to happen, see where the development will be, see what the potential bottlenecks are, and then see how this whole field as a whole will develop. And by way of doing so, we also expand the concept of closed-loop supply chains, and we can ultimately cater for cross-industry knowledge exchange, because then we can draw parallels between the industries. Okay, so this theory is rooted in closed-loop supply chain theory, and it's important to focus on the dynamics, on the driving forces, which spur the development. And a model which likewise is doing this is the model developed by Richter and Decker, and they also focus on the driving forces which push this development towards reverse logistics and towards closed-loop supply chain. So they focus on asking, why are things happening the way they happen? Who is involved, and what is happening, and how is it happening? So this is trying to capture the dynamics within this development. And pretty much the same can be done for the electric power management side. And this was my central task. Building this model, fitting this closed-loop supply chain theory to the electric power management side. And likewise, we can ask who is involved, who's part of the game, to capture who is in there. And traditionally, these are utilities, transmission system operators, of course, the customers or prosumers. So these are the central actors in this game field. And also we can ask, what is it, what is actually fed into the grid? How can we characterize this? How can we distinguish it? We can make a distinction between generation capacity and the fluctuation. Right? A power plant which is based on coal-fired power plants is much more stable than from renewable energy sources which depend on wind or sun. So there we can make a distinction. And also we can ask how this entire process of distribution, of transmission is organized. And this is a question of the grid. Which layer of the grid is involved and what are the implications for the grid? And then we can also ask, why are people doing this? Why are people buying a photovoltaic system? Why are they buying a biogas installation? And also, why are companies accepting these reverse flows? Because this is a new situation, and it was like something completely new a couple of years ago. So why is this happening? And ultimately, we can then ask, when is the loop being closed? So when are prosumers net producers, where they produce more than they consume? And when are they net consumers, where they consume more than they produce? And this is also a strategic dimension. So when are these reverse flows of such a significance that you can speak of a truly decentralized and closed-loop supply chain electric power management site? And in order to test this, so this is the main framework, because the focus is on theory building and validation, I've opted for qualitative research and case studies which focus on Germany, because Germany is at the forefront of this development, and it's also where I come from. So that was quite nearby, and I've selected 4 cases, and these are Stadtwerke Schwäbisch Hall, which is a municipal utility, and we got Novatec, which is an electric power installation company, Tenet, which is also in Holland the transmission system operator, and finally we got the Köhlers. Well, I'm afraid the Köhlers don't have a logo, but these are the Köhlers. The Köhlers are prosumers, so they have a photovoltaic system, as you can see, so they are typical prosumers, like small-scale generation, they are the prosumers. And by applying the dimensions which we have worked out in the model, by applying these dimensions to the cases, we can find out the central movements, the central development, the central dynamics which happen inside the solar landscape. And we can find out and discern the patterns which shape and transform the current landscape. So for example, we ask, okay, who is involved, and what are they doing? For example, the solar panel of the Köhlers has a capacity of 24 kilowatt. Well, that's kind of not too large compared to nuclear power plants or coal-fired power plants. And why are they doing this? For the prosumers, this is because they were looking for financial reward. It was like profit-driven. And why are the companies accepting it? Well, Tenet is legally constrained to accept it. So these are the reasons for them to accept it. And when can we speak of net production, net consumption? Well, typically the Köhlers are net consumers during nighttime, because then there is no sun, and net producers during daytime when the sun is shining. So by getting the main ingredients out of the cases, we can, for each of the pivotal topics, state what is the current state, what is going to happen, and also what are the central bottlenecks, what are the challenges. And for renewable energy sources, I found that this is already a very important topic. In Germany, this is already the second most important input share for electricity, behind brown and black coal, so this is already very important. And this trend will continue because the regulation which promotes this whole development is still in place. So it will further be promoted, and this movement is further being triggered. But what we then can observe is there are potential bottlenecks in the form of the volatility of these energy sources. Because they are very hard to steer, you cannot steer sun or wind, it's hard to steer and hard to forecast. So you need ample balancing power or storage capacity to cushion this volatility. And likewise, for distributed generation, much the same is true. It is already being rolled out in rural areas where there is a less population density and people don't consume a lot, but they have the space for these photovoltaic systems. So there is very popular, but less so in city areas. And the bottleneck, or the central caveat here, is to link these two areas, because otherwise we might waste electricity, which is generated on the land, on the rural side, but cannot be used somewhere else. And the grid in itself has been identified as a central bottleneck, because the grid has been designed to cater for these unidirectional flows, right, from generation to consumption. But now there is reverse flows, and the grid has not been designed to cater for these flows. So the grid needs to be fortified, or the whole development, the whole process the whole power reliability and quality is threatened. And the prosumers, well, this movement, again, also is likely to hold true. It will hold true because, again, the promotion which promotes this, the regulation, is still in place and is still promoting prosumers. So this is something which will indeed result to a power shift within the central actors of the energy landscape. So in total, we can say that indeed a more decentralized electric power landscape is on the way, characterized by multi-directional flows and greater volatility. And for this development, the grid itself poses a central bottleneck. So the grid has the potential to thwart this entire process and needs to be fortified because it has not been designed to cater for this development. Well, designing a closed supply chain theory and then focusing on the driving forces has helped uncover the dynamics, so we can clearly see what differentiates a traditional, conservative electric power landscape and the more decentralized and more modern electric power landscape. So by focusing on these driving forces, we can work out the differentiations, the distinctions between these two fields or these two variations, and this helps forecasting how this will develop. And as a final slide, I would like to answer the question, does it constitute a closed-loop supply chain? Well, this is a loop, as you can see, and it's closed. But the theory closed-loop supply chain, to me, focuses rather on the dynamics of the driving forces, which are spurring the development. There is no definite state in which you can say, well, okay, now it's a closed loop, and voila, that's it. It's like something development which will always evolve, and which will always involve new trades and new embodiments. But it is a dynamic system, and this theory, because it focuses on dynamics, it helped a lot comparing these industries, opening up this theory to other industries. So because this theory is a child of multi-directional flows and uncovering dynamics, it has been proven extremely fruitful by applying to other industries. So this whole body of knowledge can benefit by opening up, and as we have seen, indeed, for the electric power landscape, this means that this transformation is going to be there for a lot of time. We can now draw on 25 years of experience for supply chain management, and from what we've seen, this will hold true for the electric power landscape as well. And focusing on these dynamic and driving forces has helped uncovering that. Thank you very much.
Thank you, Andre.